Let's try some examples to see what kinds of programs should be allowed or disallowed with a typed variant of class-oriented curly. So here we've got a program where we've got a class declaration, which matches the grammar of a class declaration, and we've got a main program 10. Now, clearly when we run this program, we would just get 10. But let's see whether this is one of these programs that would not raise an error, but is still rejected by our type checker. Because our type checker should make sure that everything is going to be sensible if evaluation gets there. And in this case, we've got a get this x and a get this y. Those look good because this will have an x and y field. But then we're trying to send to those results. And whatever numbers x and y turn out to be, they're numbers. So this should not count as a well-typed curly program because x and y are not declared to be object types that would have the mdist method. So this kind of program should be rejected. How about this variant? Now I'm still doing get this, but not sending to it. That looks okay. It's a number that we're adding to plus. I've changed the y to a z though, and so you see the problem here. We don't know that there's going to be a z field when we call this method. There might be. We might actually call mdist on a posin 3D, which has a z field, but we can't be sure that there will be a z field. We can construct an example where there wouldn't be a z field, and so the type checker should rule this out. How about this variant? Now we have get this again. We have send this get y. And I think you see the problem. There is no get y method declared, so we have to check when we're type checking curly programs. We need to make sure that the methods that you use are there as well as the fields that you use are there. How about this program? We've got a get this x and a get this y. Both x and y we know will be present in this object, and we're taking those results and just adding them, so we would get a number back. That all looks good. But look at our declaration of mdist. We've declared that it returns a posin, and so that's not consistent. We need to make sure that the type that's declared for a method actually is consistent with the body of the method. So if we change that to num, how about that? That's the only change I made here, and so now everything is okay. The declared result type num is consistent with the type that we return from the method body. How about if we change our 10 now to do something finally to new posin 12? Good or bad? Well, you may notice posin has x and y, but 12 is just one expression here. So this one should be rolled out on the grounds that posin has a different number of fields than the numbers applied to new. How about if we change it? Now we've got two arguments. This new posin takes 12 and a second argument, which is itself a new posin, which has two arguments. So the argument counts all work out. And in fact, this new posin expression seems okay. It's going to give us a posin object. But the y field for this outer posin is expected to be a number, and a number is not a posin. So this is not going to be an okay program either. Nothing's going to go wrong if we actually run it, note, but the types that we've declared and the way that we're using them are not actually consistent. Let's try this program. So now I've got two methods, mdist and clone. Mdist works the way it should. It returns a number by using the x and y fields, which are present. We make a new posin given it 1 and 2. That's all good. We call the clone method with a dummy argument 0, but it's expected to be a number. And we return a posin. As declared, we actually do return a posin. The x field is a number, and the y field there is a number. This all looks good. So in fact, this program is well formed. What if I add a subclass now? Posin 3D, it's going to extend posin, and I declare the mdist method fresh down here, and it still returns a number. We call super mdist here, and we add the result of get z, this z. So whenever we have a posin 3D object, then we can call this mdist method, and those objects will have a z field. So this is all good too. How about if we change mdist to say that it returns a posin? Now locally this method is just fine. Mdist takes a number, returns a posin, and in fact we do return a posin. But a problem here is that we say a posin 3D extends posin, and in posin 3D we've said that mdist should return a number instead of a posin. So we're going to rule this out. The reason being, what we want our type system to end up doing is allowing us to use a posin 3D wherever a posin is expected. And a posin, wherever it's expected, is expected to have an mdist method that returns a number. And if we allowed this declaration, then mdist would have a result posin instead. So we're going to rule this out, and we're going to say that the general rule is that when you override a method, you need to preserve the types of the arguments and results. Okay, so I've changed mdist back so it preserves the type. Now I've got clone. Clone does not preserve the type, so this is a problem again, right? We have to check all of the methods and make sure that they all are consistent with the methods in the extended class. Okay, let's try again. Clone, it returns a posin. That is consistent with the declaration. The body of clone, however, actually makes a posin 3D. And it makes a posin 3D with x, y, and z fields, all of which are numbers, which are consistent with the field declarations of posin 3D, including the one that's inherited. The only question is, should we be able to return a posin 3D when we've said that we're going to return a posin? And the answer is yes, because the idea is that every posin 3D should be usable as a posin. So returning a posin 3D is consistent with that declaration, which means that we're going to need a notion of subtyping. That is, the type of this expression is going to be posin 3D, which is not exactly the same as the declared type posin, but we're going to say that posin 3D is a subtype of posin, and therefore this will be allowed. So just to summarize all the things that our type checker for our class-based curly is going to have to check, it's going to make sure that every time we use a class name as a type, that it's actually a declared type. Whenever there's a get or a send, we'll have to make sure that the object will actually have that field and that method at runtime. And we'll have to check that the way the result is being used is consistent with the declaration of the method argument types and result types or the field types. We'll need to make sure that we instantiate a class with new, that we provide field values that are consistent with the field declaration types. And we'll need to make sure that when we have a subclass, when we have an extending class, that any method that it overrides, it does so with the same argument and result types. Finally, we're going to have to enrich our notion of type comparison with subtypes to say that extending classes are subtypes of the classes that they extend.